Hi! This is a wonderful set of rare earth elements. Or is it? How can we be sure? I would like to test if the metals inside are what the labels claim them to be, even without breaking the glass ampules, since they are filled with argon to preserve the easily corroded metals. But how then? I think magnetism is the most simple way outside a laboratory. A magnetic field will pass through the glass and reveal how strongly the metals react to a magnet. And with a magnet as strong as my monster magnet, even tiny differences in the reaction should be detectable. Have I been scammed with this expensive set of rare earth elements? Let's find out. Big neodymium magnets are not toys. Their bone-crushing power demands responsible attention at all times. I featured this set way back in the first video of this series. Back then, in 2012. Man, time flies. My test method was very simple. Just check if a small magnet sticks to the element. That test only reveals strong magnetic attractions, and it is hard to rank the different elements' precise attraction. Now I have another, way better and much more sensitive test method. Place the sample on top of polystyrene foam on top of water. I hope this method is good enough to rank the small differences in the metal's attractions to a magnet, and then match the ranking to the official values for how strongly the rare earth metals are in fact attracted to a magnet. If my test ranking and the official ranking match, I'd say it is a strong indication of the metals being the real deal. Here's the simple test rig. Let's start with the one with the lowest atomic number, scandium. Here we go. Okay, I might have been too optimistic when choosing the distance between the sample and the magnet. After 30 seconds, the scandium has not really gone closer to the magnet. Maybe this distance will be better for my patience. Oh yes, now the scandium is clearly attracted. From counting video frames, I can measure the runtime to be 10.04 seconds for scandium. Great! We have quite a lot of samples to go through, so here are some simultaneously. Alright, praseodymium is in the lead so far. Next up is neodymium, an important element in the strongest permanent magnets, the neodymium magnets, like the monster magnet I use here. So it should be heavily attracted to the magnet, right? Well, it only just beats praseodymium. Neodymium magnets are actually mostly made of iron. Pure neodymium is not that magnetic. Here are two more samples. Whoa, europium went really fast, even though it is not known for being magnetic. Shows how strong the magnet really is, but also a sign of maybe testing too close to the magnet. When I was setting up the next sample, gadolinium, I ran into trouble. Gadolinium is so strongly attracted to the magnet that it jumps out of the groove in the foam boat, giving a less accurate comparison since it starts closer to the magnet than the first ones. Ah well, here goes nothing. Right, good thing that I, based on previous experiences, have a soft foam barrier to protect the glass. That thing flew towards the magnet. Almost the same story with the next 5 samples. For the last 2, we are back to very low attractions despite the close distance. Nice. with all the rare earth metals tested, except for the extremely rare and radioactive promethium. Here is the ranking of the ampules. Now for the truly interesting part. Does this ranking match the official scientific values for how attracted these elements are to a magnet? Let's see. Hey, that's not bad. Not bad at all, considering it is only one run and the many factors affecting the run times. The only major divergence is thulium. It shouldn't be that fast according to my source. Other than that, it is only a few swap places, and the difference between some samples is only one video frame. 4/100ths of a second, so I really need to test at longer run times for more decisive results. I ran all samples again at almost double the distance from the magnet, giving lower forces for longer run times. But filming early Sunday morning is perhaps not the best idea. I, or the magnet, messed up the camera's focus, which I didn't realize until I saw the recordings on a bigger screen. Rather annoyed, I decided to run all samples again. This time with crispy focus and better viewing angle. While time consuming, it does give us a more accurate result when I get the average time of 2 runs. Gadolinium was still by far the fastest. Not a surprise if you have seen my video on which element is attracted the most to a magnet. Gadolinium is actually ferromagnetic just below room temperature. After a short message, I will reveal the results of the longer runs and conclude if I believe the labels or not. A big thanks to all my patrons. Thank you so much for helping out. It's really appreciated and important for a niche channel with monthly quality uploads like mine. For just $1 a month, you can help me out too and get full access to all my posts on patreon.com. Link to my Patreon page in the description. Thank you. Here are the results from the 2 long runs. For the 9 most strongly attracted, it is a great result. Except for that thulium sample still acting up. For the 7 most weakly attracted, the short run result was a better match. Looks like run times above say 20 seconds will add too much randomness due to the very weak forces involved. This setup is so sensitive that just breathing near it can move the boat. The more time and the less momentum, the more any draft and turbulence will affect the results. But when I look at the results from both short and long runs, thulium really is the only big deviant. It is too fast in all cases, and it also does something the others don't. It rotates, as if the second piece furthest from the magnet is more attracted than the front piece. The 2 pieces do look quite similar, but my guess is that the second, smaller piece has an impurity in it. An impurity that is heavily attracted to the magnet. Bummer, if true. Not much I can do about it, other than look for a similar thulium sample to test if I am right. Or check if my source for magnetic susceptibility is incorrect. A PDF file I found online. I do have a physical copy of the original source, just in an older version from 1986. It is not far from the values in the 2000 edition I have used so far. Most notably, the 1986 edition lists gadolinium at room temp. Way more useful in my case and more in line with my test results. I also notice that the lutetium value seemed to be unknown back in the mid-1980s. Likely because lutetium is tricky to isolate as a pure metal. So if I had performed this test when I was 10 years old, I would have been able to estimate a much more precise value for lutetium. Fascinating thought. A minor deviation in the ranking is how samarium seems to have swap placements with cerium. Samarium should be a little slower than cerium, but in my test it is faster. Given how close the magnetic susceptibilities are, I think the samarium ampule is faster simply because it is lighter than the cerium ampule. Any corrosion of these two metals will also favor samarium, since samarium oxide is way more attracted to a magnet than cerium oxide. The last deviation is the swap ranking between yttrium and scandium. They are even closer in magnetic attraction than cerium and samarium, so even the tiniest differences in other factors will matter. Comparing the two samples, I noticed the glass ampule with scandium is slightly longer, yet it is lighter than the yttrium ampule, giving the scandium sample worse metal to glass ratio. More repelling and weighty glass, less attractive metal than for the yttrium sample. It doesn't help either that the scandium sample is less compact, with some of the metal starting longer away from the magnet. In a perfect world, all the samples should be spherical and able to rotate freely for this test, since the crystal structure in the metals might also make orientation matter. I should test if it makes a difference to start the samples in X, Y and Z orientation, but that will be for another video if you want to see it. Alright, have I been scammed with this set? Given the low number of test runs, very weak forces for most of the samples and vast number of unwanted factors affecting the results, I would say no. This set seems genuine. The ranking and run times are close to matching the expected for each element, closer than I was realistically hoping for. The only big and hard to explain deviation is the thulium sample. I still believe it is a thulium sample, just not pure enough in the small second piece. I will attempt to find another thulium sample of similar size to test if it performs closer to expected. Hope you enjoyed this video enough to click like and perhaps subscribe for more like it. In any case, thanks for watching. Bye for now.